Hi guys, now we start week 8 for topic 3. Topic 3, shear strength of soils. The topic will cover in week 8 to week 10. Our program outcomes for this subject is PO1 and also PO2. Our course outcomes CO1 and CO3. And we have CO-PO mapping, CO1 to PO1, CO2 to PO2. Now we look at the learning outcomes. At the end of this lecture, student is expected to understand the concept of total and effective stresses, pore pressure and excess pore pressure. Second, understand the concept of friction models, soil shear strength, more column failure theory, and shear strength parameters of soil. Alright, now we go for the topics pressure and stress. Okay, there are different between pressure and stress. Pressure is force per unit area. Stress is the pressure transmitted from the external phase to internal location within the materials. So pressure is force per unit area. Stress is the pressure transmitted from the external phase to internal location. Okay. A weight resting on a block causes pressure on external surface of the block and stress on internal plane in the body. Now we go for the total stress, pore water pressure, and effective stress. First, we go for the total stress. Remember word total, okay? Total stress acting at a point below the ground surface due to weight of everything lying above, for example, soil, water, and surface loading, or due to all pressure on soil sample. For example, soil or overburden pressure or water or loading. Okay, for example, you look at this. This is our ground surface and this is the total stress that we want to know. So, what we are going to do is, of course, we have the depth or Z between from the ground surface to the pressure that the total stress that we want to know about. So, total stress is equal to unit weight of soil times Z. Alright, unit weight of the soil times Z. Alright guys, look at this. Stress in the ground for a case of total stress. Okay, look at this. We have no surcharge. So means that there are no surcharge on the top of the ground surface. So if there are no surcharge, the total stress in the ground is only due to overburden pressure only. So how to determine the overburden pressure? So first, total stress is equal to unit weight times H or Z. H is depth. Unit weight is unit weight of soil. Okay, so total stress is equal to unit weight times H. Alright, this one is for cases no surcharge. For case ground below water level, for example, at lake, river, or seabed, okay, we have the water, groundwater table, or water at the top. So, and then we have the ground surface. So, how to determine the total stress in the ground due to overburden pressure and hydrostatic pressure? So, first is, look at this. This one is your pressure that we want to know, the total stress. Okay, first you have to know the depth from the ground surface to the total stress that we want to know. Alright, so and then you have the ground surface. Since this one you have water at the top, and this one is going to be unit weight saturated. Alright, so and then you have the H water, height water, and then of course you have unit weight water. So total stress in the ground is equal to unit weight saturated times H plus unit weight water times H water. H water is height of water. H is height of soil from the ground surface to the total stress. Alright, now we go for the stress for case with surcharge load. Okay, we have the surcharge load at the top. So the total stress in the ground due to overburden pressure and surcharge load. So we have the overburden pressure, unit weight time H, plus surcharge load is Q in kilopascal. Unit weight time H is also in kilopascals. So stress, total stress is equal to unit weight of soil times H plus Q. This is total stress with surcharge load. Now we go for the pore water pressure. The water in the pores of soil is called pore water. Okay, the pressure within this pore water is called pore water pressure or pore pressure. Okay, U, the symbol of U. The magnitude of pore pressure depends on the depth below the water table, the condition of seepage flow. Okay, if you look at this, this one is the soil, and now you have water, and now of course here you will have the pore water pressure. Alright. Alright, so now we go for the effective stress. This one is valid only for saturated soil. Effective stress is the amount of stress that the particles feels. The difference between total stress and pore pressure is called effective stress. Effective stress is equal to total stress minus pore pressure. Effective stress is equal to total stress minus pore pressure. Resistance to stress is provided by a combination of stresses from the solid called effective stress and pore water pressure in pore. So thus stress is equal to effective stress plus U. Effective stress is equal to stress minus U. This equation is called principle of effective stress, recognized by Tazaki. Okay, this is in the research of soil consolidation. Alright, principle of effective stress. Okay, principle of effective stress also can be written in terms of changes. Okay, look at this. This is the changes. So that the equation is given by change in effective stress is equal to change in total stress minus change in pore water pressure. Alright. Changing can be either the total stress with constant pore water pressure or the pore water pressure with the total stress constants. If the total stress and pore water pressure are changed equally, the effective stress remains constant and the soil state does not change. The excess water pressure is a condition where there are sudden increase in pore pressure within a soil due to rapidly applied loading condition or undrained condition, undrained loading. Effective stress is important for shear strength determination, bearing capacity calculation, slope stability evaluation, amount of settlement calculation, and rate of settlement calculation. Okay guys, so what is the definition of shear strength? Shear strength of soil is the internal resistance per unit area that soil mass can offer to resist failure and sliding along any plane inside it. The shear resistance of soil is a result of friction and interlocking particles and possibly cementation or bonding at particle contact. Okay, due to interlocking, particulate material may expand or contract in volume as it's subject to shear strain. The shear strength of soil is determined in laboratory as well and also as in field. Okay, for shear strength, the force transmitted between two bodies in static contact can be resolved into two components. So we have first is normal component, which is N. Another one is shear component. So what is the difference between normal and shear? Alright, so normal and shear both are perpendicular to each others. Alright, so look at that. This one is a normal stress. Okay, this one is normal stress. So you have the stress here. This one is normal component. And then you have the shear component. This one is shear. You shear. For example, this is your original soil. And then you apply normal force at the top. And then you shear. You push the soil at the top. You push and then what happen is the shear happen. So it's moved this one from original here, and then it's become this one. All right, okay, it's moved from the original here to this location. So shear refer to the sliding of one layer over another. Shear force always act along the body. The ratio of shear force applied on the surface divided by the area of surface is known as shear stress. Okay, so this one we call as the shear stress, and this one we call as the normal stress. Okay, now we go for the significance of shear strength. The safety of any geotechnical structure is depend on the strength of the soil. If the soil fails, the structure founded on it can collapse. Engineers must understanding the shear strength in order to analyze the soil stability problem like lateral pressure on earth retaining structures, slope stability, bearing capacity of foundation, and also pavement. Okay guys, look at this. This is example of shear strength failure. Okay, the shear strength failure meaning that the strength of the soil is not enough to sustain the loading at the top. Okay, so it's fail and settle like this. Okay, look at this. You can see this one is road and the soil is fail. Okay, right, look at this. This one is maybe this one is landslide, and then we have also rockfall and everything. This is slide, and then this is highway. What happened is soil is falling here, slide, and because of the shear strength is not able to sustain the loading, the own loading and also the external loading. Right, look at this. This is another failure of the retaining wall. Okay, failure, the failure of the shear strength, the strength of the soil. Right, so what happened is the retaining wall is failed because the soil is falling or fall and fail on the retaining wall. Shear strength in soil. So derive its shear strength from two sources. Okay, we have two components of shear strength. First is cohesion, okay, between particles, stress independent component. This is actually cementation between sand grain, electrostatic attraction between clay particles, and second one is frictional resistance, or we call as the friction angle. Okay, this is friction angle between particles, stress dependent component. So you should know that the shear strength parameters is cohesion and angle of friction, okay, or friction angle. Cohesion and angle of friction are measures of shear strength. The higher value of C and Phi, the higher value of shear strength. Alright guys, look at this. This is the typical shear stress curve. Typical response of soil to shearing force. So this one we're talking about shear. Alright. So this one is shear force and this one is strain. Okay, look at this. This one is in mm. So this one is strain. Stress versus strain. Figure above show the typical shear stress versus displacement or strain curve for a shearing of a prismatic element of soil under constant normal stress. Okay, for dense soil as a dense soil or dense sand and over consolidated clay. The shear stress at first increase quickly while the strain increase slowly. Okay, strain from 0 mm to 1 mm. But as the soil yield, okay, soil start yield, the strain increase dramatically while the shear stress level off and then begin to fall. Okay, this fall. So means that the shear stress is fall. Alright, and then the strain start to increase. This max value of shear stress at E point is termed as peak stress. This one is peak stress. The shear stress continue to fall at low value known as ultimate stress. Okay, the stress continue to fall at lower value. Okay, this one is ultimate stress. At very much larger strain, it refers to residual stress. Okay, this one is we call as the residual stress. Alright guys, now we look at the peak strength, critical strength, and residual strength. So what is the difference? First, peak strength is the maximum value of shear stress. Okay, for drain test, it will occur simultaneously. For undrained, it may occur at different points. So, but you have to know that this is maximum value. How about critical strength? Okay, at its critical state, soil continues to distort at constant effective stress and at constant volume. Okay, critical state correspond to stress strain typically 10% to 40%. It will increase with increasing of effective normal stress and with decreasing of water content. How about residual strength? Lower strength occurred after very large displacement. For sand, residual strength is the same as the critical state strength. Alright, so the residual strength occur after very large, or for example more than 1 meter movement, and it not usually relevant for geotechnical engineering, where generally ground movement must be small. However, on all landslide, they may have very large movement, and in such cases, the strength may already be at the residual before the construction starts. That's why sometimes the failure happen. Analysis of stress. Okay, so we will use the Mohr circle. Mohr circle of stress provide a convenient method of analyzing two-dimensional stress state. Okay, the Mohr circle construction enable the stresses acting in different direction at a point on a plane to be determined, provided that the normal and shear stress are known on any two orthogonal plane. It is very useful in soil mechanics as many practical situations can be approximated as plane strain problem. Alright guys, look at this analysis of stress using Mohr circle. Normal stress induced are sigma 1 and sigma 3. If the sigma 1 is more than sigma 3, this one is sigma 1, okay, this one is sigma 1, and this one is sigma 3. If the sigma 1 is greater than sigma 3, it will cause shear because this one is larger than this one, so it going to shear. So we call this one is shear stress. Okay, so this one is actually major principal stress, and this one is minor principal stress, confining stress. Okay, so if the sigma 1 more than sigma 3, shearing will occur. Okay, this one is shear stress. Okay, shear stress. Okay, this one is Mohr column equation. Shear strength of soil is equal to C cohesion plus stress tangent phi. Stress is normal stress applied to the soil. Tangent phi. Phi is angle of friction of the soil. Okay. Shear strength is equal to C plus stress tangent phi. Alright, this is the failure envelope look like. This one is stress, okay, shear stress, and this one is normal stress. Okay, this one is normal stress or normal stress. This one is shear stress, is tau and stress. Okay, so this one is C cohesion. Okay, this one is angle of friction or friction angle phi. Shear strength is equal to C plus stress tangent phi. Alright, so this one we call as the failure envelope. Alright, so shear strength is equal to C plus stress tangent phi. Phi is friction angle, C is cohesion. Alright guys, look at this. This is Mohr column failure criterion for total stresses. Right, so this one is shear, this one is normal stress, this one is shear stress, normal stress. Okay, so look at this. This one you have the cohesion, and then you have the angle friction, and this one is the failure envelope. So shear strength is equal to C plus stress tangent phi. C is cohesion, stress is normal stress, tangent phi. Tangent phi is angle of friction here. This one is friction angle. Alright, this one is Mohr column failure criterion for effective stress. So for effective stress, so means that you have to use the effective cohesion, effective friction angle, effective normal stress. This one is shear stress. Okay, this one is shear strength is equal to C effective plus tangent stress effective tangent phi effective. Okay, stress effective is equal to stress minus U. U is pore water pressure, right? Alright, this one is typical values of angle of friction or internet angle of friction. Okay, look at this table. This one is soil type and angle of friction in degree. Okay, sand for loose, medium, dense. So you look at this. This one is the reference of angle of friction. And this one for angular grain, this is the reference. And gravel with some sand, the value of angle of friction is between 34 to 48. For silt, the value of angle of friction is between 26 to 25. So the more value of angle of friction, the more strength of the soil. Okay, look at this. If you compare to the loose and dense, loose, the value of angle of friction is lower than dense, right? Look at this, right? So you can differentiate between loose and dense, the lower value of strength and the higher value of strength. Okay, higher value of strength, the angle of friction is higher. Alright guys, look at the cohesion. Okay, cohesion value is depend on type of soil. Okay, look at this. This one is for first case is cohesionless soil. For example, cohesionless soil is this one is C is equal to 0. It's actually for sand and inorganic silt, which is C is equal to 0. It usually is sand. For C more than 0, but phi is 0, angle of friction is 0, so there's no angle of friction here. This one is pure cohesive soil. So this one is for example is pure clay. Normally consolidated clay can be approximate at 0. Alright, for C is more than 0, phi is more than 0. For example is over consolidated clay are greater than 0. Cohesive frictional soil we call as the this one we call as the cohesive frictional soil for C and phi more than 0. Okay, so this is the type of sand. Okay, so you will have a different value of C. Okay, it may be from 0 to more than 0. All right. Alright, look at this. How will be the graph of shear stress against normal compressive stress for? Okay, look at this. For example, this one is clay. Okay, phi is 0. Okay, for clay, phi is 0. C is more than 0. So this one is clay. For sand, angle of friction is more than 0. And C is 0. This one is sand. Okay, this one is mixture sand and clay. If you refer to the cohesive frictional sand. Cohesive frictional soil. This one is mixture of sand and clay. Alright guys, now we go for the terminology. Shear stress, the ratio of shear force applied on the surface divided by area of surface. Right, shear strength is internal resistance that soil mass can to resist failure and sliding along any plane inside it. Pore water pressure, pressure within the pore water. Excess pore water pressure, change in pore water pressure. Alright, this is the terminology. Guys, don't just read the easy stuff. You may be entertained by it, but you will never grow from it. Good luck, guys.